Okay, so the exam is open book format. So obviously, I mean, you can consult your notes and stuff. You cannot consult each other. So let's um, adhere to the honor code, right? I mean, I can't monitor you, but an honor code is an honor code, right? Your signal to yourself that you have integrity. Okay, and as I said, I've specified in the course website, the first three topics will be covered. So that means incentives, communication, and information aggregation. Okay, so at this point, let me take questions from you.
So one more doubt, whether do we have to send our solutions on an email ID through which you'll be sending the question paper, or will it be like a Google Drive link where we'll have to upload our answers?
Email ID.
All right, sir.
Yes, so you have to, I'll send you a Gmail, not to my, don't send it to my regular email address, that'll collapse. So I will give you a separate email ID where you have to email your answers. Okay. So questions? Any part of those three topics that you have doubts on, want me to clarify? Nobody has any questions. This is either a very good situation or a very bad situation. I can't figure out which one. Yeah.
Sir, in the cheap talk games, if we consider if the receiver has to take discrete action, and if the receiver, there are only two binary actions. So is it possible that if the receiver gives authority to the sender, the equilibrium is the same as that of the non-babbling equilibrium in the cheap talk game?
Often yes, not always. Yeah. Okay, good question. Let me talk about it for a moment. Okay. Oh, I have to share my screen. I forgot about that. First of all, let me do that. Okay. So let's take general preferences of this sort. Receiver's payoff is action minus B of receiver minus theta squared. So you can think of B R as the receiver's bias parameter. Bias is not a good term to use. Whatever, it's some preference parameter. So this means that ideally the receiver would want to choose an action, which is the state theta plus BR, right? Similarly, the sender's preference is Okay, but let's say the actions, the only feasible actions are 0, 1. So this is a binary choice model, right? It's not a continuous choice. Okay, so so first of all, let's figure out if the sender had the authority to make a choice, what would be the decision rule of the sender? So you have the 0, 1 spectrum. This can measure both theta as well as action A. So how can we characterize the decision rule of the sender if the sender had the authority? It'll be characterized by a threshold, right? So there's a cutoff value of theta above which he will want to choose 1 and below which he would want to choose 0. Okay. So what is this cutoff value? So let's call that theta S is the sender's cutoff, right? So what is the value of theta S? Theta S is the, if theta takes that value, then the sender is indifferent between 0 and 1 as the choice, right? So that means when theta takes this value theta S, his bliss point is equidistant from 0 and 1. That is to say, his bliss point is at half. Okay. Now, what is his bliss point in general? Well, his bliss point is theta plus BR. Okay. So theta plus BR has to be equal to half. So theta S, the threshold for the sender, is half minus, sorry, it's BS. Okay. By the same token, theta R is going to be half minus BR. If the receiver somehow learned the exact value of theta, they'll use this as his threshold. Now, without loss of generality, let's assume that that BS is greater than BR. So the sender is more inclined towards the action 1 than the receiver is. So so in other words, the sender's threshold is lower than the receiver's threshold. The receiver's threshold will be somewhat higher. Okay. So let's fix this. Now, can you have a non-babbling equilibrium if they're playing the cheap talk game? Sender knows theta, receiver doesn't, sender sends a message. Now, without loss of generality, you can really restrict your attention to a binary message equilibrium. Yes, essentially, suppose the sender can change the action through his messages. He can influence the action. Like some message will lead to choice of 0, some message will lead to the choice of 1. Now, if there's some message which leads to the choice of 0, the sender will always send that message over this range where he himself wants the action to be 0, right? And if there's another message which leads to the action 1, then again, he'll send that message every time theta falls above his own threshold, right? So if there is a non-babbling equilibrium, the sender will always say 0 when he himself wants 0 and always say 1 when he himself wants 1. Okay, so the message is going to be, it's M0 over this range and M1 over that range. Okay. Now, can this be a non-babbling equilibrium? Well, it depends on where the receiver's threshold lies, and therefore what the value of the receiver's bias factor is. Now, notice one thing, given this assumption, the receiver is more, the sender is leaning more towards the action 1. So which means the receiver is leaning more towards the action 0. Okay. So if the sender sends the message 0, that means the expected value of the state is here. And the receiver's own threshold is somewhere higher, right? So the expected value will fall below that threshold. So if the message is M0, then there's no problem. Then the optimal action for the receiver is necessarily 0. Okay. The sender has an upward bias. So when he sends the low message, the receiver is not too worried about, lies and exaggeration. So the receiver just follows that message. The only problem may arise if the message is M1. So that means theta lies in this range. It lies above the sender's own threshold. So the expected value of theta is 1 plus theta s divided by 2. Okay. Now, the only question is, does this expected value of theta lie above the receiver's threshold or below? Okay. As long as it's above, our non-babbling equilibrium works. It is a valid equilibrium, right? So there exists a non-babbling equilibrium if and only if corresponding to the message M1, the expected value of the state, namely 1 plus theta s divided by 2, is greater than equal to the threshold of the receiver, which is theta r, right? And now, of course, theta s, theta r, these can be related to the parameters. You just replace them by these values. And that gives you the condition when a non-babbling equilibrium exists. And you will find that, and you can also see from the picture that this kind of non-babbling equilibrium breaks down when their thresholds are very far apart, right? So it will break down when theta r is much higher than theta s, and it is above this conditional expectation. Okay. Now, coming back to your question finally, take the two cases. Case 1 is non-babbling equilibrium exists. And case 2 is the opposite, that it doesn't. Okay. If a non-babbling equilibrium exists, notice what happens. The sender essentially always gets what he wants. In this range, he wants the action 0. He's able to induce the action 0. And in this higher range, he wants the action 1, and he's able to induce the action 1 through his message. So he's the de facto decision maker. Yes. Even if he doesn't formally have the power, he essentially has the power because the receiver listens to what he says. So if the receiver in this situation delegates, it would not make any difference whatsoever, right? We'll have the same mapping from state to action. Namely, below theta s, action will be 0, above theta s, action will be 1. Now, take the other case, case 2, where a non-babbling equilibrium does not exist. So this case, right? And half is somewhere in between. So what happens in the babbling equilibrium? In the babbling equilibrium, according to this picture, theta r is above half, right? So the expected value of the state is below the threshold. So the receiver will choose the action 0, right? Whereas if he delegates, then that'll make a difference. Then 0 is the choice over this range, but above the sender's threshold, the choice is going to be 1. Okay. Now you see a number of differences. For example, let's turn things around and look at it from the sender's perspective. Now, in the continuous choice model, you saw that the sender, at least with quadratic preferences, uniform quadratic case that we studied, the sender is better off if he can commit to honesty. Right? That was a big talking point. That if he could inject himself with the truth serum at the beginning, he would want to do so. That is not true in this kind of binary choice model, right? Because if he commits to honesty, if he does not commit, so take the case where a non-babbling equilibrium exists. So case 1. If it's case 1, then the sender does not want to commit to honesty. What happened here? I don't know. He does not want to commit to honesty, right? Because if he plays the cheap talk game, he's anyway getting his preferred action in every state of the world. But if he commits to honesty, then the receiver will get to know theta and then make his own choice. That means the operative threshold will be the receiver's threshold, not the sender's threshold. So the receiver will choose 0 whenever actual theta falls below his own threshold. So commitment to honesty here is actually counterproductive for the sender. He doesn't want to do it even if he has the option. So you see these differences, right? Once you figure out how to solve the binary action model, you see that even the qualitative properties are different from the continuous choice model.
Yes, sir. Thank you, sir.
Yeah. Next question. None? Come on, there has to be a second question at least. I don't remember if I posted last year's midterm. Did I?
Yes, sir.
This is 21920. So this number 3 was the motivation for the previous question?
Yes, sir. Yes.
Okay. Actually, I have the written solutions to last year's question paper, so I will post that. I just found I have the solutions to that one. Okay. Any other? You're all comfortable with solving, a standard cheap talk model, uniform quadratic case. I give you parameter values, right? Often a question starts like that, and then it gets, the subsequent part gets, maybe gets a little twisty, but you should be absolutely, be able to solve a partition equilibrium in your sleep. So
So,
yes.
with respect to solving the regular cheap talk model, when
Right.
we start writing our receiver's belief structure, how do we actually write it? Like the maths part of it, I had a doubt. Like I'm able to calculate the intervals, but I am not able to understand how do we write the belief structure. Like
don't worry too much about writing the belief structure, right? So if there's an interval partition equilibrium, right, then every message corresponds to some interval. Okay. Now, if it's uniform distribution, then the conditional expectation, given that the message has told the receiver that theta lies in this interval, the conditional expectation of theta is basically the midpoint of that interval, right? So don't worry too much about a formal statement of the beliefs of the receiver. Okay. You have a number of intervals. Each interval corresponds to a message. If the message mk is heard, that means it's the kth interval. So the receiver's belief will be that theta is now uniformly distributed within that kth interval. That immediately implies that the expected value of theta is the midpoint of that interval, which immediately implies that the optimal action of the receiver will be the midpoint of the interval.
all right.
Yeah, I know in the notes I have written a cumbersome, this is like when I was setting out the model at the very beginning, I wrote a sort of somewhat inelegant expression for beliefs with integrals, etc. Forget about it, right? I mean, we all know what it means. Okay. Any other questions? Everything in the problem set clear? Where's the problem set? So you should look at some of the essay type questions and the solution, what I've written down in the solutions. As I said, the solution is not the 100% ideal response. It's a little cryptic, but I've written down the main points that you need to write down. And you need to sort of remember all the points, right? Every question will have a number of relevant points that you need to capture. I'm trying to pick one of these questions to illustrate what I mean.
So can we do question number 10 as well of the problem set?
Okay. Question number 10 basically is the censorship game. Yes. So sender 1 knows the state. Sender 1 has 0 bias, and sender 2 has positive bias. So it's a special case of the censorship game where the original sender and the final receiver, they have no conflict of interest. They have the identical preferences, right? The problem is that the guy sitting in the middle has a bias, B, positive bias. Now, if you look at the solution, so first, there's this argument that, there's no fully revealing equilibrium, because if the original sender just, naively tells the true state, the player in the middle, the second player, will obviously distort that. So we can try to find partition equilibrium, yes, and And then if you look at the second paragraph in the solution, right, this was a critical step we did for the censorship game. We can always, for every equilibrium, there's an equivalent equilibrium in which in equilibrium, there's no censorship, right? So the original sender resigns himself to the fact, he's trying to send a message to somebody who has identical preferences. He doesn't, as such, if he could communicate directly, he doesn't want to game it, doesn't want to lie or exaggerate or distort. But his message can only be channeled through an interested party, right? So whatever be the equilibrium, yes, the guy in the middle, the censor, conveys some partition to the final receiver or the decision maker. Without any loss of generality, you can assume that the original sender can foresee this, and he also communicates to the second player in terms of the same interval. Yes. So this means that when sender 2 learns the state is in the interval, in the kth interval, he prefers the midpoint. So then we come to this incentive constraint of the censor, the second player in the middle. Okay. So yes. So the censor, when he learns that theta falls in the kth interval, he has a choice between reporting that faithfully or reporting upwards, right? He has a positive bias. His bias is to go higher. So obviously we have to only check for incentives that he doesn't want to lie upwards. So what you have to make sure is that when the first player, the sender, sends him the kth message, he doesn't want to lie and say, I've heard the k+1th message. Okay. Now, what guarantees that? Well, if he faithfully conveys what he has heard, then the cost he'll suffer is B. The optimal action will be B distant away from his own bliss point. Okay. What if he exaggerates? What if he lies and says, I have heard the k+1th message? Well, then the receiver will choose this xk+1. This is the action he chooses after the k+1th message, right? Which is the midpoint of that interval. And from that, you have to subtract his bliss point, right? He has actually heard the kth message. So his bliss point is xk+b. Yes, xk is the expected value of the state and his bias to that. So this is what he would ideally want. Okay. So if he lies upward one step, then the action is away from his own bliss point by this distance, right? What you have on the right hand side. And if he does not lie, if he faithfully says that, I have heard the kth message, then the cost he suffers is just B. So as long as the B is less than this, his incentive constraint is satisfied. Okay. So that's what you have. Now, also when we were discussing the censorship game, we saw that, these incentive constraints are hardest to satisfy at the very left end. Okay. So if it holds for the first interval, which is the shortest interval, that if it's true that when he hears that the theta lies in the very first small interval, that he doesn't want to lie upwards, then he will not want to lie upwards for anything further to the right. Right? I sort of gave you the logic for that. So once you have this inequality, you just have to apply it to k = 1, right? And that'll give you the condition that is needed for some equilibrium. Yes. And because there's no conflict of interest here between, um, the sender and the receiver, the first player and the third player. Remember that, when in a two-player game, when the bias is zero, the mutual bias is zero, they have identical preferences. All interval equilibria are symmetric, right? The asymmetry of the equilibrium arises only because of a positive bias factor. So when B is zero, if you want to construct a two interval equilibrium, the intervals will be of equal size. Same for 3, same for 4. So in this case, this special case with a sensor sitting in the middle, the whatever be the equilibrium will be of every interval will be of equal length. Yes. And so once you have this inequality, notice that this is twice the size of each interval. So this is so our inequality boils down to the bias has to be less than 1/4 times 2 times the length of each interval. Okay, and that's what gives us this last inequality. Okay, any other questions?
Sir,
Yes.
so in the bias had a problem.
Yeah.
Could you please just explain what do we mean by skeptical beliefs? It is not clear to me.
You're asking in general or with reference to a specific question from
So in general.
Yes, skeptical beliefs um, are the worst possible beliefs, right? So suppose the message says, um, so let's say we're talking of, the unknown state of the world is the monetary value of what is being sold. Okay, capture some quality, and so the number represents the monetary value to the buyer, right? And the buyer wants to pay the exact monetary value, no more and no less. So suppose the message says that the monetary value lies between 60 and 80. Okay. Now, the buyer will pay the expected value after hearing this message. So for example, if after hearing this message, his belief is that, whatever interval has been specified, it's a uniform distribution in that interval. Let's say, just to pick a random belief. That means after this message, he'll be willing to pay 70. Yes. Now, what is the worst possible belief that will lead him to pay the lowest price? The worst possible belief is that if the message says the value ranges between 60 and 80, then it's the lowest possible value with probability 1. Right? So out of all the kinds of beliefs that he can form after hearing the message that it lies between 60 and 80, the worst possible belief from the seller's perspective, the one which will lead to the lowest action or the lowest price being offered, is the belief which puts probability 1 on the lowest value, 60 in this case, right? So that's what we're calling skeptical beliefs.
Okay, sir. Thank you.
Right? the general idea is that the message itself may be vague, but of all the possibilities created by the message, remember the message can't be an outright lie. It gives a range of possibilities. Of all the possibilities created by the message, the buyer selects the one which is worst for the seller, leads to the lowest possible action or price. Yeah.
Sir, in the unanimity rule,
Yeah.
when we did the case of when size is very large,
Right.
and we show the probability of sigma is tending to 1, and the probability of convict given innocence is greater than 0,
Yeah.
and the third probability is probability of acquit given that guilty is greater than 0.
Right.
So I didn't get it why the third inequality is greater than 0. The probability of acquittal given guilty is greater than 0.
See, the model is symmetric. Okay. So that's not anything very deep. So if we can prove that probability of um, conviction given innocent is strictly positive, right? Even as n goes to infinity, even in the limit. That means that this is the wrong decision in the innocent state. So that means probability of acquittal given innocence is strictly less than 1, right? Now, I mean, the models we're considering are symmetric. I mean, the result is a little more general than that, but sticking to the symmetric structure, symmetric meaning kind of the mirror images, right? So this probability is also the probability of making the other kind of wrong decision, right? No, sorry. I misspoke. No, the voting rule is not symmetric, it's unanimity. So sorry, I take back what I started saying. Anyway, we proved this, okay? This is one kind of error. In the innocent state, you take the wrong decision. But there's another kind of error, right? Which is in the guilty state, you choose to acquit. And so in the paper and in our discussion, we also kind of gave some reason why both of these error probabilities are strictly greater than 0 or bounded away from 0, even as n goes to infinity. Yes, the reason we have to talk about them separately is that it's not a symmetric model, right? Conviction requires all n votes, but acquittal requires only a single vote, right? So potentially they could behave differently. Potentially one could be bounded away from 0 and the other converges to 0, but none of them do converge to 0. That's what it shows. Does that answer your question? And maybe you ask something else, but these are completely different objects. And so the result that each is bounded away from 0 is basically 2 results.
Sir, I get it, like why these two will be bounded away for 0.
Yeah.
But in particular, when we are doing the case of Vg is equal to 1 and Vi is equal to sigma, and then we are showing n tend to infinity, then also will both the error will be bounded away from 0.
Vg, you mean the gamma g? You mean this object in the notes?
Uh, Sir, like Vg, simple V, that I will I will go for convict after seeing the guilty signal, small v okay. I guess the type 3 equilibrium or type 2 equilibrium.
What is Vg? Are you asking why these results are true? What is the logic behind these asymptotic results? Is that what you're asking?
So, sir, can you please open up the slides?
You want to screen share?
Yes,
Oh,
and if you can open.
okay. Let me open up the slides. So this is information aggregation. Okay, strategic voting. All right, I'll be scrolling down. Tell me where to. Okay, this thing you're saying?
Yes, sir. BG. Sir,
Yeah.
the result I was mentioning, that is on the last 4 to 5. So 2 slides back, I guess. So, yes, sir. This one, the
Okay.
third.
Yeah. This is the relevant slide.
Yes, sir.
Okay.
So,
So what?
sir.
Yeah.
Sir, here we will convict after seeing the guilty signal as well as convict after seeing the innocent signal.
Well, you have to be very careful about limits, right? That's not literally true what you just said. So, uh, so after seeing the guilty signal, conviction vote is with probability 1. That's throughout. What is sigma I? Sigma I is the probability of voting for conviction after seeing the innocent signal. Now, what we are saying is that in the limit, this becomes 1. It does not literally become 1. Take any arbitrary large n jury size. This sigma is not literally 1, but it gets closer and closer to 1 as you increase n. So this is only for the limit. A sequence of numbers can approach a limit but never actually hit the limit.
Yes, sir.
Right? So that's the difference. Limits are tricky, but you have to be aware that we're talking of limits. We're not talking that, after 1 million, sigma suddenly becomes literally 1. That's not true.
Okay, sir.
Right? So it's a little more subtle. It's not happening because after a certain jury size, everybody always votes for conviction no matter what and goes home. No. But almost always everybody votes for conviction. Just to counteract the fact that a single vote will spoil any attempt to convict.
Okay, sir. Thank you, sir.
Okay, questions? So again, you should be, you should sort of not shut down your minds. You should keep your thinking hat on. Like if you look at the problem set, one of the questions, the numerical questions are usually what you have done, but with a slight twist maybe thrown in here and there. So for example, in this part 8C, I do a little perturbation on the bias. Instead of a constant bias, the bias is B plus C times theta K. So the bias itself, the distance between the bliss point of the sender and the receiver becomes a function of the state. It's not a constant number anymore, right? There's a constant part, but there's also a state dependent part, which is C times theta. Now, there's no need to panic if you find something like this, which is slightly off the track that you have covered. you just remember the logic that, how did we solve the constant bias case? We said, okay, there's a number of intervals, and at the cutoff points, the points where you go from one interval to another, the indifference condition has to hold, right? So with this slightly new kind of bias, all you have to do is to apply that same logic that, okay, if the sender is to be indifferent at every cutoff point, what has to be true? So that will give you your difference equation, and you can just solve that and find the equilibrium. So remember the fundamental logic of each of the exercises, the voting models, the cheap talk models, what have you. And then it shouldn't be too hard. Okay. All right. So there doesn't seem to be too many questions. So I'll take that as a good sign. I'll put a lot of probability weight on that state of the world. I will post solutions to the 2020, the last year's midterm, and that includes that binary action version of the cheap talk model, which I discussed today, but I'll have the full written answer for you.
So,
Yes.
just regarding the pattern of the paper, is it going to be like a more than 30-mark paper since we 3 hours, and that will be like brought down to 30, or do we get options? The students want to know.
How
And
does it
many
matter?
questions?
What is one of the first theorems you learned in consumer theory in Micro 1? The utility functions remain. You can make positive affine transformations. It makes no difference to anything, right? To a utility function. So will it be 100 scaled down to 30? Will it be? Don't worry about it. It's absolutely inconsequential. Yes. Your strategy to study, to attempt the questions should be absolutely immune to what the grading scale is. Yeah.
Sure, sir. Yes.
Eventually, it's going to carry 30% weight. That's all that matters.
All right, sir. Thank you.
Yeah. Okay, guys. Good luck for Saturday. All right. So I'll